Hello, everyone. My name is Eric Kekula, and this is a presentation from my book on economics of planning. This presentation is based primarily on chapter 1, which introduces a number of thinking tools. And what we'll do in this presentation is introduce the concept of a marginal value function, compare that to a total value and an average value function, derive total benefits from a marginal benefit curve, and do likewise with total costs derived from marginal cost curve. We'll introduce the concept of consumer surplus and of producer surplus and of deadweight loss, and we'll show how marginal analysis can help us to find or identify an optimum. So let's get started. The place to start thinking about a marginal value function is a total value function. Likewise, if we compare it to the average value function, which is a kind of sibling of the marginal value function, in the sense that the total value function spawns each of these. And so we can derive the average value function from a total value function. We can derive the marginal value function from a total value function. And so they're like sibling functions. So to get into that in just a bit more detail, here I've depicted a kind of a total value function. There are any number of total value functions one might use. This is just one that I'm using to help illustrate. And I encourage you to think about how one might represent all of the ideas introduced here if the total value function had a different shape. That's actually a very useful exercise to undertake. So we'll look first at the average value function and how it's derived from total value, because that's familiar to everyone, I think. Average is something that we use just really in daily discourse. And we all know that the way to calculate an average is just to take a total and divide it by n, where n is the number of items over which this applies. Now, in terms of the geometric or graphic representation of this, be interesting to note that this formula, this average is just the total divided by n, has the interpretation of the slope of a chord that runs from the origin to any particular point on the total value curve. So let's look at N3, for example. The corresponding total value is T at N3, which in this particular diagram happens to correspond with T of N1 as well, due to the symmetry of this shape. And so notice that the slope of this chord is given by the rise over the run, which in this case is the total value, Tn, divided by n. Well, Tn divided by n is the average. So it's the slope here that represents the average. So if you're looking at a total value function, it's the slope of that chord running from the origin to any given point on the total value function. That slope has the interpretation of an average. Now, for the particular diagram that we have here, we can see that the average is falling, because here's the chord corresponding to N1. It has a fairly steep slope. If we move over to N2, although the total value is higher at N2, the average is lower than it was at N1, and we can see that because the slope of the chord going from the origin to the total value function at n2, that slope is lower than it was for the one at n1, and likewise for at n3. And I think you can see that as we move to the right, starting from the origin, move along the horizontal axis, that average curve is going to be declining steadily. And so that's what we show down here. We have this blue line that runs down, and in this case, it happens to run down in a linear manner. That just reflects the nature of the total demand, the total value function from which it's derived. So this is the corresponding average value function. Now, because this is the average value function, any point on the curve represents the average value. So while in the graph up above, which is the total value function, the average value is represented by the slope of a chord. If we come down here, the average value is simply represented by the point on an average value function. Now, that's the way we derive an average value from a total, and this is a very nice kind of graphical representation of that. It's also possible to go reverse direction, and we know that as well. If we just take that formula for an average and sort of turn it around a bit, we find that if you have the average and you multiply it by n, that's a way of recovering the total. Well, the geometric interpretation of that is just going to be the area of the rectangle that's defined by the origin and some point on the average value function. So each point, whether it's the one corresponding to n1, so that's the average value at n1, or the one corresponding to n2 or n3, each of those, any point on the average value function, will define a rectangle. The rectangle may be square, as in the case of this one here at n2, but the area of that rectangle is the total value. And you can, again, convince yourself of that by reminding yourself of this formula, that if you're given the average value, which is the height of any of these, because this is the average value function. If you're given the average value, you multiply it by n, which is simply the width, then that corresponding area, because height times width gives you the area, that area corresponds to the point back up on the total value function. So it's a nice sort of geometric visualization of what is a fairly routine and even mundane sort of calculation, calculating an average from a total or recovering a total value from the average, either by dividing by n or multiplying by n. So that's good. And in a sense, that's nothing new except perhaps the graphical representation of it. But now we can do the same thing or apply the same kind of thinking to introduce this idea of a marginal value function. So we've got the same total value function here, but the definition of the marginal value function is really the change at any point, the rate of change, which is really given by the slope of the tangent at that point. So again, if we focus on n1, n2, n3, we could be focusing on any other points, but just for purposes of illustration, if we see n1, that the slope of that tangent is positive. Well, if we move to n2, the slope is 0. And if we move to n3, the slope of the corresponding tangent is negative. And so we see that same relationship here. At n1, it's positive. At n2, it's 0. And at n3, it's negative. And it's negative to the same extent that n1 was positive, again, reflecting the symmetry here. And you can convince yourselves, I think, that this marginal value function will start off at a high positive value, as it does here, and steadily decrease. It's positive, 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 but it's decreasing, finally reaches 0 here at N2, and then becomes increasingly negative as we move beyond N2, beyond N3. Now, the way to recover the total value function from the marginal value function, this is something that we'll see is very useful in economic analysis. The way to recover the total value from the marginal value function is to take the area beneath the marginal value curve, or between beneath or above, but relative to the horizontal axis. So, for example, at N1, here is the marginal value. Well, we've indicated the marginal value here. So the total value, if we want to recover what the total value is, it's going to be the area of this polygon. And as we move to N2, if we want to recover the total value at N2 just by looking at the marginal value function, it's going to be the area inscribed by this triangle in this case. So at any given point, you'll see we have if we're looking at the horizontal axis and the marginal value curve, it creates this corresponding area. So for example, if we move further now to N3, we find that the area defined by this is now beneath the horizontal line. It's negative. So that means that we actually need to subtract this area from what we had before in order to get back to the total value. Now, the observant among you may notice that this triangle right here and this triangle, they're identical, or they're symmetrical here. And that, again, reflects the symmetry in our original total value function. And so that tells us that the total value at N3 is essentially this complete value. So as I've shown here, the light blue, the slightly darker blue, minus this darkest blue, this navy blue here, gives us the total, helps us to recover the total value. So we have to subtract that. This comes in negative. And that's consistent with the interpretation here. This is saying that as we move further, we're falling off. The total value is falling off. And that's why this is indicated as a negative. So that introduces the ideas quickly. Now let's turn to how we use this for economic reasoning. And to do this, I'm going to first start with a loaf of bread, which I find to be sort of the most intuitive way to think about the relationship between marginal and total. If we're thinking, for example, of something like marginal benefit, as we get more and more and more of something, say slices of bread, as I've indicated here, if we're looking at the benefit, well, that first slice of bread, we're really hungry, and so it's got a certain benefit. The marginal benefit is the benefit of an increment. It's the marginal benefit is like an incremental benefit, or the benefit associated with one more of something, right? So that's what we mean by being on the margin. And so the benefit derived in this particular example, we've got a marginal benefit curve that falls off, diminishing marginal benefit. You may have heard of that expression, and it's a very common idea, kind of common representation of a marginal benefit curve in many cases. So if we've got declining marginal benefit means that as we get additional slices, well, yes, we're still hungry, but not quite as hungry as I was. So the benefit of having one more is not quite as much as it was previously. That's the basic idea of diminishing returns. And so as we just saw earlier, the way to, if we consume this much, then the corresponding total benefit is given by the area beneath the curve. But this applies just as well to marginal costs. And so here's a marginal cost curve. And again, the area beneath the area beneath the marginal cost curve is indicative of total cost, because we're adding cost, adding cost, adding cost, adding cost with each increment. And if we stop at a given point, then we look at the corresponding area as the total cost associated with that. Now, there are some related concepts that we can look at. One that you'll likely encounter in dealing with economic issues is that of consumer surplus. And consumer surplus you can think of as a kind of a net benefit to consumers. And let's give an example here. Suppose there's a cost of some good. So we're going to go out, maybe that we're out buying slices of bread as we were earlier, but we've got this diminishing marginal benefit. Now, we're going to keep purchasing if this is indeed the representation of our marginal benefit, and this is the price, which in effect plays the role of a kind of a marginal cost to the consumer, because if the consumer is a price taker, in other words, the consumer just has to accept that this is the price of bread out on the market. Well, if that's the case, then, and if this is indeed a representation of the marginal benefits of consuming this good, of purchasing this good, the consumer is going to purchase up until that point where the marginal benefit no longer is sufficient to justify paying that cost. So we know from what we just saw earlier that the total benefit, the total gross benefit, is the area beneath this polygon. But this square described here, or this rectangle, is the total amount that the consumer pays. So there's a kind of a cost, a total cost due to the price of this good that the consumer pays, that's represented by this rectangle, but the gross benefit was more than that by the amount of this triangle, which is determined as consumer surplus. So you can think of it as a kind of a, not exactly a profit, but this net benefit, this surplus that does come to the consumer, because the idea is that for some of these intra-marginal slices of bread, the benefit to the consumer exceeded the costs that they're paying. And that's wherein the surplus is derived. A similar idea applies to producer surplus, that if we've got a marginal cost curve, which functions as a kind of supply curve in this context. And by the way, in this context, this marginal benefit curve is functioning as a demand curve. We'll talk more about that in subsequent presentations, but it's useful to keep in mind that there is a very, very, very close correspondence between a marginal benefit curve and a demand curve, and likewise between a marginal cost curve and a supply curve. But sometimes they're not the same, and we get into some interesting economic issues when those diverge, as we shall see in later presentations. So the producer surplus then, if indeed this is the marginal cost curve, and they're looking at the same price that the consumer was looking at, well, then the producer is going to keep bringing supply to market up until the point where the price that they receive by selling the good no longer is no longer less than the amount that they'd receive. So once the cost on the margin to the producer of bringing extra goods to market exceeds the price that they get, well, then they're going to stop. Why would I bring something to sell for $10 if it costs me $12 to produce? I just will stop once my marginal cost hits $10. And again, the same kind of reasoning we use to describe this consumer surplus applies here to the producer surplus, that if we look at the intramarginal slices of bread, so to speak, as we're in here, the price received by the producer exceeds the cost of that marginal product. And so, of course, it's worthwhile. And there's that little bit of surplus. And so this area represents the total value of that surplus to the producer, hence producer surplus. So one last thing we'll look at here is how to apply this same kind of reasoning now to thinking about the notion of deadweight loss. And this is a kind of graph that we will see in many of the different applications. So this particular diagram is actually one that's worth really taking note of and thinking about how it applies under many different examples, whether we're talking about traffic congestion or land use zoning or housing or so many other applications. It's essentially this same kind of diagram showing up again and again and again, which is one of the reasons I really want to emphasize this at the beginning so that we know to be on the alert for this, because in effect, we don't have to learn each of these different application areas starting from scratch. What we do is simply know that this marginal analysis can be applied to any of these areas. And it's just a question of sort of getting the fit right and sort of making the story conform to the graphs that we're telling, and likewise making the graphs conform to the story that we want to represent. But we can use the graph for thinking in a reasonably consistent and precise and analytical manner. And it can also guide our data analysis. So in this particular graph, what we have is marginal benefit curve declining, as we see here, and a marginal cost curve rising, as we see here. And what's indicated here is, if we're again comparing points N1, N2, and N3, at N1, there's deadweight loss, because the marginal benefit, if we think, well, suppose we were at N1, if we were to do a little bit more than N1 of whatever this activity is that's represented on the horizontal axis, it could be buying loaves of bread, slices of bread, or it could be adding additional open space to a given city. Any number of things that horizontal axis may represent. But if we're doing it at a level of N1, if we're at a level of N1, we can see, well, why stop here? The marginal benefit exceeds the marginal cost. So let's do one more. Well, if we do one more, the marginal benefit still exceeds marginal cost, and one more, and one more, and one more, and one more. And that continues right up until we get to N2. And at N2, it's no longer the case that marginal benefit exceeds marginal cost. So there's no point in proceeding. Now, let's compare this to N3. If we were at N3, it's the same kind of reasoning, but in the opposite direction. If we're at N3, the marginal cost exceeds the marginal benefit. So if we were at N3, we say, well, let's let's step back a bit from N3. Let's reduce the level of activity because the cost of these items on the margin exceeds the marginal benefit. So why bother? So we do one less and then another one less and another one less. And it's only when we get back to N2 that we find that the marginal cost no longer exceeds marginal benefit. So this shows that anything for this particular graphical representation of marginal benefit and marginal cost, it shows that anything less than N2 is not enough. Anything more than N2 is too much. And so N2 is in fact optimum. And if we were at N1, this shaded area represents the deadweight loss, which is a kind of foregone net benefit. Because at N1, we're foregoing the extra benefit that we would have had we extended out to N2. And the same reasoning applies if we're looking at this from the perspective of N3. This deadweight loss represents the extra costs we're bearing above and beyond benefits. So it's a kind of negative net benefit that we can shed if we were to simply stop doing so much of this activity N. So they all point to N2. So one of the things that we'll be looking at, a theme that's going to occur throughout the book, through the different presentations, is thinking about when do markets bring us to this optimum point where we essentially get rid of all the deadweight loss. And what we'll find is that sometimes markets will bring us to that optimum point, and that's a glorious thing. But in many other occasions, markets will not bring us to this optimum point. And so one of the things that we'll be wrestling with, and this will be a subject of a different presentation, is this distinction between the equilibrium outcome of a market or some other social process, social or even physical process. So there's this notion of what is an equilibrium outcome versus what is an optimum outcome. When the equilibrium and the optimum coincide, we tend to be happy. When they don't coincide, we're essentially looking at cases of market failure, is a generic term that we apply to many such cases where the equilibrium outcome and the optimum outcome differ. And so this particular graph sets us up to do a lot of storytelling around that. And that's some of what we'll be doing with the chapters to come. See you then.